Okay, distance, rate, time problems show up in a lot of different varieties, and I'm going to start with the most basic model. And we want to use the equation distance equals rate times time whenever possible. And this one is just a very short problem. A car travels 221 miles, that's the distance. In 3 hours, that's the time. 3 hours and 15 minutes, that's 3.25. Sorry about that. And what is the rate? That's what we're solving for. So if we were to just divide each side by 3.25, we would find out that the rate is 68 miles per hour. Now that is the most basic of problem styles, and usually the word problems you're going to deal with don't deal with just a plain old D equals RT. So what I'd like to do is describe a general procedure to use to attack these different types of word problems. Now, take a look at the following. Sometimes you have two cars, planes, trains starting at the same place and traveling in opposite directions. And the question is, how long until they're 500 miles apart, or something like that. Or sometimes you have two cars, planes, trains, whatever, in cities that are so many miles apart, and they're traveling toward each other. And the question is, when will they meet? Well, in both of these cases, you are given a total distance, either a total distance of how far apart they will be after they travel away from each other, or a total distance they start at until they or from each other until they meet each other. So I like to call this the total distance pattern. And when you're dealing with the total distance pattern, you have the distance of vehicle 1 plus the distance of vehicle 2 adding up to a total distance d. Now if distance is equal to rate times time, we're going to have rate times time for one car, train, plane plus rate times time for another car, plane, train, and I'm using capitals and lower so we know they're from different vehicles, is equal to a total distance d. And that right there is one equation that will govern two different patterns of problems. Now, there are a couple other problems that we deal with. Sometimes we have someone who goes on a hike, they hike up a mountain, and then they have a return trip down the mountain. Now that is a return trip model where the distance up the hill and the distance down the hill are the same. Sometimes you go to Grandma's house and then you come back from Grandma's house. Again, you have a return trip. There's another model where two people start at the same place, but someone gets a head start driving somewhere, and then someone leaves maybe an hour later and they drive a little bit faster, and the question is, when do these two cars, or when does the second car catch up to the first car, or when do they overtake the first car? Now in both of these situations we're dealing with a same distance. And so if I want to say distance 1 is equal to distance 2, I can rewrite that as rate times time for a distance is equal to rate times time for another distance. And notice here that this covers a wide variety of different patterns that will show up. And so when I start doing distance, rate, time problems, if it's not a short, simple, use a single D equals RT type of problem, I will ask, am I dealing with a total distance or am I dealing with a same distance? And that will tell me what equation I want to write at the top of my paper. I don't use the distance, rate, time tables at all. These equations will solve 95% of the word problems that you're going to encounter. So let's practice this in our first problem. A woman hikes 1 mile per hour faster down a trail than she does on the return trip. Return trip uphill. Okay, that tells me I'm going to be dealing with the same distance. And so I'm going to have rate times time for one equals rate times time for the other. Now the first one was downhill, and sometimes it helps to label that, and the second trip on the return is uphill. Okay, let's see what we've got. Downhill, she goes 1 mile an hour faster. So shouldn't my rate maybe be an r plus 1? And then a regular r rate on the uphill trip? It takes 3 hours to get to her destination. That's downhill, 3 hours. The return trip takes 6 hours. Notice how easy it was to just put those values in, and we're trying to look for the downhill speed. Okay, here we go. Well, let's solve this equation. On the left we have some distribution to do, so this will give us 3r plus 3 equals 6r, and I'm going to choose to subtract 3r on each side of the equation, and that will give us 3 is equal to 3r, and therefore r is equal to 1 mile per hour. Now, in these problems, it's very important that you always reread your problem to make sure that the answer matches what we're looking for. This one asked, what is her downhill speed? Well, r is the speed up here when we're dealing with uphill. The downhill speed was r plus 1, and so 2 miles per hour will be the r plus 1, which is going to be downhill. And so we're looking for 2 miles an hour for her trip downhill. It kind of makes sense because when you're traveling downhill, you go faster. This problem is a little bit different and it doesn't show up very often, but I'd like to do it for you to show you some of the tricks that can show up. Two canoes travel down a river starting at 9 o'clock. One canoe travels twice as fast as the other. After 3.5 hours, the canoes are 5.25 miles apart. This is not a total distance, but a distance they are apart. One is traveling faster than the other. Here's the other one. They're traveling in the same direction. And what we have here is how far apart they are after those 3.5 hours. So this is actually a difference in their distances is 5.25 miles. And therefore, we're going to have distance for one minus distance for the other is equal to 5.25. Now, one of them is traveling twice as fast as the other, so its rate will be 2r, and the other one will have a speed of r. And as far as time goes, we have a 9 o'clock start time, which is extra information there only to confuse you. And both of them are traveling for 3.5 hours, and no one had a head start. So let's substitute in 3.5 for the time on each of these vehicles or canoes. And let's see what we have. 2 times 3.5 is 7r minus 3.5r is equal to 5.25. And combining like terms on the left, we have 3.5r is equal to 5.25. Let me slide that up there. Dividing each side by 3.5, we can now find out that r is equal to 1.5 miles per hour. And the problem wants the rate of each canoe. The other one's going twice as fast, 2r, which will be 3 miles per hour. We don't see this pattern very often, but it does show up. Usually it's RT plus RT equals D for a total distance, or RT equals RT when you have the same distance, but every once in a while, like in this problem, we have plus or minus. When the distance apart is given, we're going to subtract instead of add and have RT minus RT is equal to D.